Hi everyone, my name is Alex. I'm an engineer and my passion is design, development and prototype production of all sorts of engineering solutions. In this episode I'd like to share with you some recently designed and made shop tools which I designed and made to convenience my life a little more. It's not convenient enough just yet. Among those tools are a chamfering tool, mostly for sheet metal, but it can be used on all sorts of parts. A threading adapter tool for the mill. What else? We have a short taper gauge that is very easily made in any shop with scrap material for short taper gauges like lathe spindles or chuck flanges. What else? Yeah, you'll see along the way. So if you're interested in this sort of thing, join me. So I adopted this 4-jaw chuck here as an addition to the other chucks I have on my MCO V13 lathe. And this chuck comes from the estate of my late friend Albert Klocker, the former master mechanic of the village I live in. And it is not the most precise chuck there is. I think it's from the end of the 1960s, but still I want to keep it as sort of a memento from Albert. And it's in a fairly good condition, so it's more than adequate to do roughing work on large stock. So only thing I had to make was this chuck flange here to fit my MCO V13 lathe. And the difficult part about making such a flange, as you all know, is to make a fairly precise short taper bore on the inside that fits the spindle nose of the lathe as precisely as possible. So precise meaning this one has to touch and spindle face and the flange face have to touch. So there are several ways to gauge the short taper, but I want to show you how I did it. And I've made up this very petite and very pretty gauge. So in a gauge contest it would win first prize for beauty. But it's fairly simple, and that's the bonus of it. It consists just of bearing balls, 5 bearing balls, some rod and this bolt here. And it's all welded, or better said, just tack welded together. And the way it works is, this is my MCO chuck, which is pretty messed up from the previous owner, but I could stone that out, but that's not the point here. So the way it works is you rest these 4 balls on the face and the bore and then take a reading. And I've set this dial indicator here, which is a 10 micron per division indicator, so that it reads 40. So the reading is also very consistent as we go along the circumference. And let's take this as a reference and keep in mind the 40. Compare this to this Bison chuck here, where we see that this one is short of 10 microns, tighter. So the reading is more, which means the bore is tighter. And I aimed for the same dimension on the flange I made, so this should also be short of 10 micron tighter than 40. It's about 5 microns tighter than 40. So this one is in dimension between the Bison and the MCO short taper. So that's the way this gauge works. The reading is very consistent, as you can see, around the circumference. And as we take a re-reading, it's also very consistent, even though this gauge looks like it comes from a Stone Age camp or something. I may have touched the indicator a little bit, but still, I guess you get the point. When I made this gauge, I was also pressed for time and a little lazy, so believe it or not, this bolt here that holds the indicator in place is only tacked, as you can see, in one location, which is here. And it's a very strong tag, as you see. But still, what I want to point out here is that this gauge, may it be as ugly as it is, but it works really consistently, as you see, and therefore trustworthy. So thanks a lot to Stefan Gotteswinter for reminding me to show this gauge. I hope it may be helpful for the one or the other among you in a certain machining task. So short taper gauge. The next tool I made for my shop, or for myself, and which I want to show you, is this one here. And what it is, let's take a look. What it is it is a threading adapter with a friction clutch. So it is made from a broken well-done holder, which I hard turned and modified to accept this friction clutch and bushing arrangement here. And this accepts these tapping holders or tap holders, and they have ground grooves on them which insert into these ball tracks on the inside of this readily available machinery bushing. These bushings, that's on the inside here, they're called, I think, in English they're called rotation ball bushing, but I'm not perfectly sure of that. And you see these roller tracks holding bearing balls. They ride on these grooves of this shaft here, which comes along with the bushing, of course in greater length, but here shortened and drilled, reamed and broached for the tap. And the effect of this is that the tap holder can slide in and out completely free and still transmits the threading torque into the tool holder. And this is adjustable on this tool here with the aid of this friction clutch. So in the softest setting, you see it can be fairly easily turned, and the harder you set it, the more torque it can transmit, the more maximum torque it can transmit, that is. So these shortened shafts, I just drill and ream them, and then I broach a square hole into them, which is a tiny bit larger than the standardized square drives of these taps. And these shafts, they are standardized, so it doesn't matter which supplier you have, they should always fit this tap driver. So let's see how that works. Let me just go to the coordinate of the M6 hole. And what I want you to note is I've clamped this piece here in a cantilever fashion so that any axial push or pull that would act on the tap during the tapping process would be visible as this bends up and down quite intensively. So this avoiding of axial push or pull is the main thought behind this tool here, and I'll talk a bit more about this in just a minute. Let's see how it works first. So I set the friction clutch to a quite soft setting, and now let's see. So you see the friction clutch already disengages. I set it a bit stronger, still a bit stronger, and it moves out completely free. I don't have to move the quill, and you also see the piece I'm threading, it didn't bend at all, or you should be able to see it doesn't move vertically at all, which is an indicator of the fact that there are no axial forces acting on either tap or workpiece during the tapping process. And this is what I wanted to achieve with this tool, because you may say now, why should I make such a tool? It's not necessary. I can thread, or I can even power tap with the machine quill and have the quill move in and out. And of course that's possible. But in my opinion, or as I find, the quills on different machines, they move in and out quite differently. The one with more friction than the other, the one with more spring pull than the other. And with large taps, this may be of no consequence. But with the small taps, and in my opinion that's M6 or 1/4 inch and smaller, this may affect the threading process quite a lot, because if there's a lot of friction in the quill or a lot of spring force in the quill, return spring force, this is an additional force that acts on the tap during the threading process and affects thread quality quite a lot. And particularly with the small taps, for example, this here is an M3 with its drive insert. So let's check out how this works. It works basically the same, but how it performs. Of course I don't show power tapping here on the camera because this is more controllable, but power tapping is pretty much the same as you can imagine. So some oil, and I open the friction clutch up to the minimum setting. Let's start the tap, and you see it moves in and out completely free. We should have absolutely almost zero axial force on the tap, which should improve the tapping quality and reduce the risk of breaking the tap quite a lot. So for small taps and small threads, I find this is a very, very nice addition to the shop. And if you say you can do the very same thing with a spring-loaded center and a tap holder, of course you can. But I don't like the spring-loaded centers on small taps because they don't ride that well on the tap holders, the tip of it I mean, and they have no hole in there. Of course we can hard drill a center hole in there, but this makes everything a little more complicated. And also the spring-loaded center requires a bit of height, which sometimes may be lacking in the setup you have or on the job you have. So I like this addition very much. The only downside to it is this rotation ball bushing. Yeah, I think that's the name. This can be readily sourced. However, it has to be modified, and its housing is hardened. In this particular one I have here, the housing is hardened. So everything has to be hard turned. Also this weld-on holder here, I had to be hard turned and hard threaded. So it was a nasty piece of work, but a nice tool to have, I think. And here is these two threads we just made. And I hope it is in focus. You can see a very clean and tear out free lead in, and the same on the smaller one, on the M3 one. I hope you can see that in focus. Here we go. Okay, so very clean lead in. That's the benefit of having no axial push or pull during the threading process. So, quite recently I made this Oxy-Acetylene Cart here. Because formerly I had my gas bottles just tied to the wall. And you know how awkward this is when you need them somewhere else. So I had to build this cart to calm down my nerves, basically. And the design process was quite involved because I wanted it to have some features like storage space for flux and solder, or maybe your lunch, I don't know. Also, the bottles are in there in a tilted way, so the security against tipping over is higher. Then this cart has these two patches here for when I transport it in my van. I can safely ratchet strap it against the back wall. This cutout, or this notched feature here, is for when I have the large TIG machine in the van and this unit. Then this can be bricked together like Lego and ratchet strapped to the back wall, so everything's safe and secure and nothing. There's no chafing between the carts. Then these posts up here, they are holding features for the pressure regulators. So when I transport this in the car, I can put the caps on and still have a place to safely secure the pressure regulators, these posts here. What else? Yeah, you see this cart has all these cutout features here, and I grew so tired of deburring these cutouts because I want to have them almost radiused for when you grab it this way. I grew so tired of deburring this that I had to think of a tool that makes this easier, more consistent and more professional. Now you may say, Alex, don't be stupid. Just leave away the cutouts and don't deburr them, and then you don't have to deburr them. Yeah, right. But I wanted this thing to be as lightweight as possible. Firstly, when I transport it in the car, to cut down on the fuel consumption. And secondly, because in case of an emergency, this thing can be worn as a backpack. There are slots here and here, and you can put some ratchet straps through them and wear it as a backpack. Of course, when these bottles are full, the whole thing weighs roughly 40 kilograms or 80 pounds roughly. So it's quite a heavy thing, but you know, they told me that's what an infantryman should be able to carry. Let's hope such a case of an emergency will not turn up so quickly, but you know, I live in the Alps and we've had cases of emergency before when you're happy about having equipment on location. Well, as I said, I grew so tired of deburring all these cutout features that I finally made this tool here, or to be more precise, this part of the tool. This other part here is just a pneumatic grinder spindle. It's a BX type. It's a BX R3040 with a cylindrical body. And the cylindrical body is really nice here on this tool because it provides a clamping feature for this collet. And this part of the tool provides the guiding so that the chamfer has a very consistent and uniform size. So what you do is you insert the tool into this guide body and you clamp the collet, and basically then you're good to go. The tool is oriented 45 degrees with respect to the table here. This is the table along which you guide the workpiece, and this pin here is the guide pin which provides the guiding feature, or the size defining feature of this thing. What we have here is a clamping screw, and this here is the adjusting screw. And watch the guide pin. You see that turning the adjusting screw moves the guide pin along the cutter in and out to free more or less of the cutter length and therefore increase or decrease the chamfer size more or less. These notches on the adjusting screw, they're spaced in a way so that Turning the screw 1 notch means increasing the chamfer size 0.1 of a millimeter. And then we clamp it again. This thing here is just a counterweight, because this hole deburring tool can be used in two ways. On the one hand, you can clamp it in the vise and use it for small pieces, or you can use it by hand if you have large sheet metal pieces, for example, or large work pieces, for example sitting on the workbench or on sawhorses. Then you can hand guide this, and this thing acts as a counterweight so that this is balanced and you don't have to hold it down onto the workpiece. You just have to feed it or guide it along the edge of the workpiece. The major benefit of this tool is that it uses, where do I have it? It uses straight or cylindrical carbide cutters. These are quite cheap, particularly if you buy cutters that have no cutting features on the face, because it's not necessary for this purpose here. And the nice thing about the arrangement of this tool is you can almost completely consume the cutter until you have to use a new one. So this is an old cutter, and you can probably see that this is dulled all the length of the cutting edges. So this tool is a very cost-effective way of using carbide cutters, quite in contrast to using conical cutters, because then usually only a small fraction of the cutting edge can be consumed until you have to buy a new one. So that was the major thought or in the design of this tool here. And how is that done? Well, you just loosen the collet, and then you can slide the cutter in and out of the tool. And this way you can consume almost all the cutting edge. So let's see how that works. So I've clamped it in the vise here, and there's no danger about damaging something in between there, because it's very beefy on the inside. Complicated but beefy. So let's see how that goes on this sample workpiece here. So works quite nicely, or really nicely. Let's see about that hole or this thing here. I hope that's in focus. But you see, it's a really consistent size of chamfer all around this cutout feature. And it doesn't matter if it's steel or aluminum. Of course the forces are higher in steel, but with the carbide cutter that works in steel just as well. And the second way of operation is to use this freehand, and let's see about that. So let's try to chamfer the second side of this cutout here. We just chamfered before this one, this side down here. Hope that's in focus. So, all in all, I think you can understand me. I love this tool as an addition to my workshop. It's heat treated, so therefore it's hard on the surface and it's corrosion resistant. So what more can you wish for in such a tool? Alright guys, this wraps it up. Thanks a lot for your interest in this video. I appreciate your time. All the best for your machining projects and hopefully see you next time.